last time we started stoichiometry and we did mole to mole conversions, right? Starting with 1 mole of our reactants or 1 mole of our products, whatever, 1 mole of a substance, and converting to moles of another substance or grams of another substance. Today, we're going to take that even a step farther, and we're going to say if we start with the number of grams of a substance, how can we convert directly to the number of grams of another substance? Okay, can we go directly from grams to grams? Is it a one-step process to go from grams of ammonia to grams of water? No. The only place that we can compare two different substances is in what part of our T-chart? The mole ratio step. Very good. Okay, so in our T-chart, when we're doing these conversions, the only place that we can go one substance to another substance has to be moles to moles. Okay? So we want to find out how many grams of nitrogen monoxide is produced if 12 grams of oxygen gas is combined with excess ammonia. Okay? You don't have to write all of these little bullets down. This is just kind of our step-by-step process of what we're going to go through to get to our final answer. But this is our overall goal. Okay, so in our T-chart, the first thing we're going to do is write what we know. Okay, we're looking to start from 12 grams of oxygen, and we want to find out how many grams of nitrogen monoxide can be produced. What does it tell us when it says we have excess ammonia? Does that mean anything to us right now? Right now, it really doesn't. It just means that we have extra of this compound. So when we're doing our reaction, it means that the oxygen gas is going to run out first, right? When we combine these in the correct ratio, oxygen gas is going to run out first. So ammonia is not going to have an effect on our reaction. Okay, that's going to mean something to us a little bit later in the chapter. But for right now, not a whole lot. Okay, so 12 grams of oxygen gas. My goal is to go from grams of oxygen to grams of nitrogen monoxide. Okay, but can I go directly from grams to grams? No. So where do I need to be heading? What does my process need to be? Grams to moles. Good. So if we want to go grams of oxygen to moles of oxygen. Okay, so what would go right here? 32, right? The molar mass. Okay, and moles gets the 1 when we're going between grams and moles, right? In the mole ratio step, it doesn't always get the 1. Every other time it does. So now we're done with grams of oxygen, and we're left in moles of oxygen. Is that where we want to be? No. So we need to go from moles of oxygen now to moles of nitrogen monoxide, right? That's going to be the step where we make our switch from moles of O2 to moles of NO. Okay, do we see now why it's so important to carry the units and the name of the compound in our T-chart? If we don't do that, you're going to end up flipping these top to bottom and you're going to get confused. So where do these numbers come from? Yeah, good. It comes from the balanced chemical equation. And since we're looking at moles of O2, what coefficient goes right here? 5. And then on the top, what is it? 4. Good. These numbers are coming directly from the periodic table. So we're done with moles of O2. We've crossed those out. Now we want to go from moles of O2 to, moles of NO to moles of what? No, backwards. To grams of NO. There we go. Sorry. Okay, so our last step is to go from moles of nitrogen monoxide to grams of nitrogen monoxide. What does the mole get here? The 1, good. And what's the molar mass of nitrogen monoxide? 30, good. Very good. Okay, now we've made sure all of our units cancel. Okay, if your units are not opposite or diagonal of each other, they don't cancel, which means it's not going to work. Your units have to be opposite of each other. So we multiply across the whole top, divide by the whole bottom. Okay, when you divide on the bottom here, you need to do divided by 32 divided by 5 or divided by parentheses 32 times 5 close parentheses. Okay, that's really important. If you take it divided by 32 times 5, it's going to divide by 32, then it's going to take that whole answer times 5. Okay, so when you have two things here in the bottom of your T-chart, you either need to put parentheses in your calculator or you do divide by one, divide by the other. Okay, that's really important. So I got about 9 grams. Okay, any questions here? All right, we should be thinking about the ratios here to see if that answer makes sense, right? We started with 12 grams, and this has a 5-to-4 ratio. So if we started with 12 grams of our 5 mole substance, shouldn't we be coming out with less than 12 grams of our 4 mole substance? Okay, that ratio only works because their molar masses are similar. Okay, if the molar masses aren't similar, then we have a little bit different. But just try to get a little bit of an expectation of what we should be looking for in terms of number scales here. Really big number, really small number, stuff like that. Okay? Okay. Let's go ahead and balance that equation. This is our question right here. But we need to balance that equation first. What do we think it is? Give me the coefficients. Oops. All right. Tell me again. 1, 1, 1, 2.
1, 4, 1, 2.
Oh, 1, 4, 1, 2. Okay. Sorry. 1, 4, 1, 2. Yeah. Okay. Yeah. Looks good. All right, how many grams of, can somebody tell me what that is called? What's SN? 10. Sorry. No, what's this one right here? 10. No, tin's a metal. When we have a combination between metal and nonmetals, we don't use our prefixes. Tin for fluoride. Right? It's got to be a +4 on tin because fluoride is a -1. All right, little side step there. Okay, what is this compound right here? Hydrofluoric acid. Very good. So we're starting with 12.8 grams of hydrofluoric acid. We're going to go from grams of hydrofluoric acid to, what do we need to go to?
Moles.
Moles of what? Good, same compound. Okay, moles here gets the 1. Hydrofluoric acid's molar mass is 20 grams per 1 mole. Good. So we're done with grams. We're left in moles of hydrofluoric acid. From there we want to go moles of HF to what? Good. Moles of tin fluoride. Okay, and our mole ratio was 2 to 1. Yep, you're right. Thank you. Thank you, thank you. I'm looking at the wrong compound. 4 to 1, that would make a difference. Okay, and then we want to go moles of tin fluoride to grams. What's our molar mass then of tin fluoride? 194.7, and moles gets the 1. Okay, so now I'm done with moles. Done with moles of that. Left in grams of tin fluoride, which is what I want. Multiply across the whole top, divide by the whole bottom.
31.15.
Okay. Perfect. 31.15 grams. All right, questions there about those 4 steps? The good news is that's as complex as our T-chart will get, okay, is 4 steps. We're not adding any more steps to that, Okay, it'll only get simpler from there. So those are the most complex ones that we'll do. Okay, from grams of one to grams of another. Any questions there? Okay. Same balanced equation for every question, so you only have to write down the equation once and then go ahead and balance it. You're going to try these on your own. Oops. One of them's mole to mole, one of them's gram to mole, one of them's gram to gram. Just posted up here. 2.4 moles, 13 grams, and 83 grams.
College chemistry be easier here.
So we've done gram to gram. Now we're going to switch to molecule to molecule. What's the only thing that changes here when we go molecule to molecule? Yeah, we use Avogadro's number. What do we not have to use when we go molecule to molecule? Good. We don't have to use molar mass or grams. Very good. Okay. So this is the same balanced reaction from your previous problem. So you don't have to rewrite that down if you don't want to. You can just do it right underneath the last one. Nice. I'm sorry, not as your very last question. We did this balanced reaction a little bit earlier. Okay, so I think you told me it was 1, 4, 1, 2. Okay, thank you. Okay, so you used this reaction a little earlier. If I start with 4.21 times 10 to the 23rd molecules, how many hydrogen molecules are formed? Not how many hydrogen atoms will there be, how many hydrogen molecules. So what's the difference there? What's the difference between a hydrogen molecule and a hydrogen atom? A molecule is H2, right? And a hydrogen atom is just one single H. We won't ever solve for hydrogen atoms, right? Because they can't hang out by themselves. So when we say hydrogen molecule, that means we're looking for H2 hydrogen gas molecules. Okay? So we write what we know. So if I want to go from molecules, what do I need to go to? Moles. Moles gets the 1. How many molecules are in 1 mole of anything? Good. Okay, so I'm done with molecules of 10. I'm in moles of 10. And I want to go to what? How do I get to hydrogen? I go to mole ratio of the hydrogen. I accidentally wrote hydrofluoric acid. I want H2 right here. Okay, so our mole ratio between tin and hydrogen gas is 1 to 2. It's kind of squished up there. Okay, but hopefully you get the point. So we're done with molecules of tin, we're done with moles of tin, we're done with moles of H2, and we're left with molecules of H2. Do we see in our teach right here that we're going to end up multiplying by Avogadro's number and dividing by Avogadro's number? So do we really need to plug that into the calculator both ways? No, we can take that times 2. So our mole ratio is 1 to 2. Okay, now do we see how we would apply it if it asks for us to go from grams to molecules instead of molecule to molecule or gram to gram, right? Do we see how we can interchange those conversions anytime? Hopefully. Okay, I hope that you should be able to apply those principles across all your conversions.